Hi, I want to talk to you about polar coordinates today. Okay, polar coordinates is a different coordinate system. We use Cartesian coordinates most of the time, but there are sometimes when polar coordinates are needed for drawing certain graphs, like spirals, okay, or other circular formed graphs. Okay, and I'm going to illustrate that a little bit later on. But before I do, let me just talk to you a bit about how the coordinate system works. In polar coordinates, instead of an x-axis, we have what's called an initial line, and it's labelled L. And instead of an origin, we have what's called a pole. We still label it O though, and I sometimes mistakenly call it an origin, but it's called the pole, okay? And that's a initial line. We don't have any vertical scale, notice, okay? So that's basically a blank set of axes, okay? I sometimes put a vertical line on anyway, because it's helpful, to be honest, okay? And you'll see some of the other examples I put on later on, I'll be having vertical scales, okay? But how do they work, okay? Now, in terms of Cartesian equations, we normally reference that using x-y coordinates, we say, where the x coordinate stands for the horizontal displacement from the origin and the y coordinate the vertical displacement from the origin. But in polar coordinates, we don't do that. What we do is we find out what the, whoops, let's just cheat and extend that a little bit. What we do is we find out what that length there is, called the modulus, okay? And we work out what that angle there is, sometimes called the argument, and we express polar coordinates in the form r theta. So we still write the brackets for coordinates, but we have r for the modulus and theta, okay? R sometimes we call a radius, okay? That's one of the reasons why it's called r, okay? Theta is the angle that this, call it a vector, okay, or line, makes with the initial line, okay? And an angle is in the anti-clockwise direction. And we usually use radians because radians are the preferred angle of measure, okay? You can either go from 0 round to 2 pi, or you can go from 0 to pi and then 0 to negative pi, okay? It's up to you, okay? Certain situations mean it's better sometimes to do 0 to negative pi. The principal argument, that is sometimes called. Now let me just give you an example. Suppose we have the Cartesian coordinate. I'm always using 3, 4, aren't I? It's just 'cause it's so simple. Okay, suppose we've got the Cartesian coordinate 3, 4. How would you convert that into polar coordinates? Okay, well, what you do is you just imagine, because you don't always draw this, you see, a right angle triangle, and that length there is 3, that length there is 4, and you've got what r is straight away, see, it's 5. Okay. In general, I'm going to write a generalisation here. You've got x squared plus y squared equals r squared, because that is your x value, and that is your y value, so x squared plus y squared equals r squared. Okay. Also, in general, you can write down that x is equal to r cos theta, and y equals r sine theta. Because if I just get rid of the 3 and the 4 for a moment, it's always messy when I use my fingers. Yeah, cloth is always, I just hate having to reach down all the time. And we'll leave it there and see what happens. Yeah, there we go. Because that is x and that is y, and so yeah, x equals r cos theta, and you'll know that from mechanics work. Okay, all this gets linked together, doesn't it? So fantastic. Yeah. You've got to feel sorry for year 7s, haven't you, year 8s, year 9s, because I never see how maths gets linked together. You've got to kind of make the effort and get to sort of year 13 really, before you start seeing it all coming together. Okay. And yeah, this angle, well, that's the inverse tan, isn't it, of 4 over 3. Inverse tan of 4 over 3. Calculator. Okay, so radians mode, great. Inverse tan, 4 divided by 3. And I should remember that because I did it just a few hours ago, but there you go, I don't remember that. 0.927. 3 significant figures. Okay, I was going to do the dot thing. Yeah. Yeah. Right, so that's what it is in polar form. Okay, I'm going to highlight those because often we convert between not only coordinates but equations. Okay, we convert between equations in Cartesian and polar form. You've done parametric equations. Okay, well sometimes we have polar equations. Okay, so that's effectively a third different type of equation that you've actually come across now. There are other coordinate systems as well, intrinsic coordinates, which have kind of gone out of fashion now. I'm not sure why, but yeah. Polar coordinates is a really big one. Okay, Let's have a look. I'm just rubbing this off just so I can give you some examples of what some polar graphs look like. Okay. Right, in polar form, okay, we need to know simple graphs like this, r equals 5. What does it look like? What does the graph look like? Okay. Every time I do one of these, feel free to pause the video, have a little think, and then unpause it, and then just see how it all pans out. Okay. Well, notice that this equation is independent of theta. Okay. What it means is no matter what the angle theta is, the value of r, which we sometimes call radius, is 5. It's kind of giving it away for you, really, isn't it? You get a circle. Let's try and draw a reasonably good circle. Hey, there we go. Okay. Remember, pole, initial line. Okay, you've got a circle of radius 5. Okay, and that's it. Okay, because you can see at any point on this curve, r is always 5 and it's independent of the angle. Okay, what is the Cartesian equation of that? Well, do you remember the? I'm going to write down here. One of the relationships I wrote down was this: x squared plus y squared equals r squared. Okay. Well, if I were to square both sides of that, you'd have r squared equals 25, yeah? And then r squared, you just substitute in x squared plus y squared. Okay, equals 25. And that's your Cartesian equation, which you probably knew anyway. Okay, but that's a simple example for you. Whenever you've got r in a polar equation, if you can find some way of getting r squared, you can just substitute that in straight away, and it's really, really simple. Okay, or vice versa. If you've got a Cartesian equation and you've got x squared plus y squared somewhere, great, just substitute in r squared. So that's quite simple. So that's your first example. Okay, the circle. So in general, you could say that's the equation r equals a is a circle where the centre is the pole and the radius is a. So that's in general. Okay. What about this? Okay, where you've got something like this. Theta equals pi over 3. Think about that. Right, well, this time you notice it's independent of r, but the angle must always be pi over 3. Okay, angle must always be pi over 3. So when we draw it out, you've got your initial line there, pole. So the angle is always pi over 3. So it's something like 60 degrees, isn't it? So something like that, yeah. How far along the line do we do it? Well, it goes on forever. Okay, so that means is the value of r could be anything you want. It could be 0, it could be 1, 2, 3. R is never negative, by the way. R is never negative. It's always positive. Okay, the reason is because of the Pythagorean theorem to do with lengths. Okay, so r is always positive. Okay, so it extends infinitely in that direction, never in that direction. That's what we call a half line. You might think that makes no sense. You know, I mean, it's a line, not a half. Well, in mathematics we call it a half line because a half line extends indefinitely in one direction only, but there's an end to it. A complete line means in both directions. Okay, so there's a couple of simple equations for you and a couple of simple graphs for you. Okay, come right up, I'll give you some more.